So this video is going to talk about how to find volume using calculus. The kind of fun part about this is they're very hard to draw, but so I'm going to try and explain these best I can using pictures, and we'll see how this goes. So we have the disc method and we have a washer method. So if you think about a disc, this is going to be, normally it'll be drawn sideways, but I'm going to draw it kind of standing up here. So this would be kind of our disc, where this would be the top of it. It's almost like a cylinder, except for it doesn't have to be a cylinder. It could be something that looks like this too, where it's more of a trumpet type shape. But the idea of it being a disc is it's solid. I can cut it into little discs all the way through. Then we have a washer method. This is the same thing as this, except for it has a hole in it. So if I were to see if I can do a picture of this. I'm not very good at drawing these, especially where people can see what I'm drawing. So imagine like a tree trunk almost, but it's hollow all the way through. So I don't even know if you can understand what I'm showing you there. But so a washer is basically a 3D shape with a hole in it. So I'm going to use kind of something here to what I'm going to talk about. So this would be considered solid. Okay, imagine, so this would be a disc using the disc method. It's completely solid, there's nothing in it. However, so let's imagine like this bottle of oils. We know if we were to take everything out of it, the outside is glass, but there's a hole in the middle. So that would be using the washer method. And the idea is we're finding the volume of the substance, whether it be everything that's inside or the amount of glass it would take to make the bottle. So we've got two different formulas that are kind of dealing with this. And for the disc method, we really only have one function that we deal with, but keep in mind we go from A to B. There's a pi here, so it's kind of like pi r squared. If you recall, is the area of a circle, and then integrating it actually takes it and makes it that volume. And then here we've got one radius squared minus the other radius squared. So it's taking the outer radius, so it's taking the whole thing and subtracting out the middle thing. And then once again, it goes through the same thing. So here's kind of our key. F of x is the radius of the outer disk. G of x is the radius of the inner disk. All right, let's look at an example. So let R be the region bounded by the curve f of x equals x plus 1 squared, the x-axis, and the lines x equals 0 and x equals 2. Find the volume of the solid of revolution obtained by revolving R about the x-axis. This is where it gets very difficult to draw, so we're going to try. So here's 0, and we're going to imagine that 2 is over here. So we know that I'm revolving an area that's going to be in between these things. Okay, so that takes care of this and this. Then I'm going to say, okay, I'm dealing with the x-axis, so that's this right here. And finally, I've got my curve here. So y equals x plus 1 squared. All right, if you recall what this looks like, well, and actually we're going to go from 0 to 2, so we might as well just plug in some points. So if I were to plug in 0, 0 plus 1 is 1 squared, so I'd get 1. And then 2 plus 1 is 3, and 3 squared is 9. So I'm going to come up here, and I'm just going to mark this as 9, and then 1 would be somewhere down here. So my graph would go here, and it is a quadratic, which means it's kind of got a parabola shape. So it's part of a parabola, but it's not an entire parabola yet. All right, here's where it gets difficult. So this is our area that we're revolving around. So imagine a solid block of wood, and then you have a bit, imagine like a router bit in wood shop, that this is what the edge looks like, and you're going to basically kind of drill it around the circle. So if I were to mirror it down here, this is where it gets kind of tricky for me. So you can kind of see that it's almost like a trumpet. So think about the bell of a trumpet, but it's completely filled in. So here's the bell of our trumpet that's solid. So we haven't drilled out the inside yet. All right, this is what we're trying to find the volume of. And we are going to be, since there's no hole, we're going to be using this one. All right, so I'm going to write that formula here just so we have it. So the integral from a to b pi f of x squared dx. All right. Our a to b is once again our x. So we know we're going from 0 to 2 because that's where our graph went to, and that's what it tells us here. So we're going to integrate from 0 to 2. My pi is a number. I'm going to throw that out front. And then f of x is this equation right here. So I'm going to have x plus 1 squared. So that's what I'm going to integrate. I'm going to go ahead and simplify this. So I'm going to have pi, the integral from 0 to 2, of x plus 1 to the 4th dx. Now you have a couple different options here. We could FOIL this out 4 times, then integrate it, or we could use our substitution. I'm going to use the substitution just because we just learned that and it isn't that bad on this one. So I'm going to say u is x plus 1. That means du is dx. So I'm going to go pi. Then I've got u to the 4 du. And I want to show you kind of a trick. I haven't really shown you this before. If I convert these to u and I'm putting numbers in them, I don't actually have to convert them back. These are my x values. I can change these to u values. So my u here, so I'm going to have 0 plus 1. 0 plus 1 is 1. 2 plus 1 is 3. So once I have this all substituted in, I'm done with this over here. So I'm just going to integrate this. So I'm going to have pi times u to the 5th over 5. And I don't need a plus c because I'm going from 1 to 3. So pi times 3 to the 5th over 5 minus pi times 1 to the 5th over 5. And then I'm going to go through and I'm going to do that. And I'm going to leave the pi out of it for now. Here, let's pull this up here. So I'm just going to do 3 to the 5th divided by 5 minus 1 to the 5th, which is 1, divided by 5. Forgot the 1. All right, so math inner inner. I could go with the decimal. It really doesn't matter. Either one. They're both fairly nice things. So I'm actually going to go with the decimal. So I had 48.4, and remember I didn't put the pi in. So I have 48.4 pi. This would be my volume. I could go ahead and multiply those, which would give me an approximate answer of 152.05. And that is okay as well. But that is our volume. So it's kind of using the same ideas that we've been doing, except for now applying it to a situation where we might need the volume. All right, another example. Okay, the region R is bounded by the graph of f of x equals the square root of x and g of x equals x squared between x equals 0 and x equals 1. What is the volume of the solid that results when R is revolved about the x-axis? All right, first things first, let's sketch a graph. And once again, we're between 0 and 1. And I do like to spread these out so I have some space to actually draw my picture. All right, f of x equals square root of x. That looks like this. g of x equals x squared. That's going to look like this. And I know because of how the parent functions work that they do cross here, but what if you didn't know that? So once again, let's figure out where these cross. What we would do is we'd end up squaring both sides. So I'd have x to the fourth equals x. Subtract that over. So x to the fourth minus x equals 0. Factor it out. So x cubed minus 1 equals 0. So x equals 0 and x equals 1. So 0 and this would be 1. That's where they intersect. So my area here is this one here. And this one is extremely hard to draw. I'm going to do my best to help you out here, but it's a very difficult one to do. All right. Okay. So like I said, not the greatest of drawing. I guess the easiest way to think about it is it's kind of like a flower pot or a weird vase where the glass is extra thick right there in the middle. So if you turn it this way, you can kind of see the three-dimensional shape here is just very difficult. Or imagine the edge of a potato right here, and you're carving out this piece out of the middle. Just this cone, you're curving out a cone. And that's what what part of the potato is left, that's what the shape looks like. So it does have a hole in the middle is kind of the part we're getting at. This one is y equals square root x. This one is y equals x squared. That's important to know. All right, we're gonna go from 0 to 1 because that's what we found our intersections to be. We're still gonna have our pi. Do I need to remind everybody of the formula? We're going to be using this formula right here. So if you don't have that written down, pause, write it down, or have the notes pulled up so you can see it because I will have this scanned on the computer later. All right. Then we're going to have our outer function. Well, our outer function is this one right here because it's going to be the outside of our shape, which is the square root of x. So I'm going to have my outer function squared minus my inner function, which is this one right here. It's the inside squared, and that's what I'm integrating. All right, so let's simplify this. I'm going to throw my pi out front. The square root squared is just x minus x to the fourth dx. So as far as integrations go, this one's actually a fairly simple one. So I'm going to go ahead and do this. So 1/2 x squared minus 1/5 x to the fifth. And it is okay if you have x squared over 2 and x to the fifth over 5. That's the exact same thing. But it's going to be this times pi. Mommy. And then we're going to be doing this from 0 to 1. All right, so let's leave the pi out here. We're going to do this. So if I plug in 1 squared, this is 1, this is 1. So really I'm going to be left with 1/2 minus 1/5. And then if I plug in 0, basically 0 is going to turn to 0. So I'm going to do 1/2 minus 1/5, which would be 3/10 or 0.3 times pi. So my area here will either be 3 pi over 10, you might have 0.3 pi, or you could multiply this out, in which case you would end up with 0.942, and any of these would be correct as far as the volume would go. So I actually really enjoy doing these. The drawings are kind of tricky, which I enjoy. I don't know why, but hopefully this helps you narrow down how you're going to find volumes using integrals. So our integrals do find areas and volumes so far. And remember, derivatives found slopes of tangent lines. So calculus really has some far-reaching applications to them, but especially knowing how to do integration to go through and find the areas and volumes. And as you move higher up into calculus, you do even more with this. So I hope that helps, and good luck.